Okay, so I wanted to work through a couple of kinematics problems in case it would help to see a couple, for example. And I've chosen two from the Giancoli textbook that look like they involve a slightly different thought process. The first one is number 37. A ball player catches a ball 3.0 seconds after throwing it vertically upward. With what speed did he throw it, and what height did it reach? Now, when tackling a problem like this, it's important to look at what you're trying to find. So what do you want? Well, what I want is the maximum height. That's h. And I also want the speed, the initial speed. So that's vi. I'm going to leave the subscript off and use it when we get to the formula. Now, it's also important to think about what actually happens in the problems. A lot of places they say you need to draw a sketch, but I can't draw a sketch on Microsoft Word that's very detailed. So let me just think about it out loud for you. So the ball is going to go up, and it's going to come back down. And it takes 3 seconds to do the whole thing. Now to think about the maximum height, that's obviously not the beginning and the end, because it goes up and then it comes down. So when we analyze the problem, we really only want to think about half of the case. This is a free fall problem, or rather a hang time problem, where it goes up and then it comes down. So if it's a hang time problem, we want to consider the first half or the second half. And I think, and it's symmetrical because we're neglecting air friction. That was part of the directions. I just left it out. Neglect air friction. So if you find the initial speed, you also find the final speed. Doesn't matter which one you choose, but for me, I find it easier to think about the way down, because on the way down, the velocity, the distance, the acceleration, they're all going down. So I'm going to consider the way down. And you know to split it into two pieces because it's a hang time problem. So I'm going to consider the way down, and we want h and vi. What do we know? Well, first of all, we're going to say positive is down, because everything's moving down. That's pretty easy. We know the time for half of the trip is 1.5 seconds. And what else do we know? Well, it doesn't say we're on Earth, but I think we can assume we're on Earth because I don't know if there's ball players in other places. Maybe there are. So if it's on Earth, the acceleration is 9.8 meters per second squared. So we know a and t, and if it's the way down, vi is 0. Now don't get confused about this. We want the initial speed with which the object was thrown up in the air. So this is the same as the final speed. This one that I've written here is vi. This is the speed at the top of the flight. So it gets thrown up in the air. Sorry, there was music outside. I wanted to try to avoid that. So it gets thrown up in the air, and it stops at the top. And that you know from your understanding of what happens with hang time problem, that the ball goes up, it stops, and then it comes back down. So the speed at the top of the flight is 0. So what we want is we want the equation that looks like distance equals 1/2 at squared, and that's going to give us the maximum height. And then when we want the final velocity, we can use the definition of acceleration. So I'll show you what I mean. Let's look at the maximum height first, and we'll pick the formula that we want to use. So I'm waiting for it to open up here. Open. Open. There it is. All right. If we want the maximum height, that's x, and we are going to use the information that we know, which is going to be this one. X equals vit plus 1/2 at squared, where if we're just considering the way down, the initial velocity is 0, so that's 0. Plus 1/2 at squared, that's going to be 1/2 times 9.8 times t squared, which is 1.5 squared. So that's 1/2 times 9.8 times 1.5 squared. You guys are just going to have to deal with the music. It's not stopping. So that's 11.025 meters. Okay, so then that's the height. Then we want to find the speed that he threw it with. So that's going to be the same as the speed with which it hits the ground. So for that one, we're going to use, and again we're opening up this equation editor. That's going to represent the final speed, so we're going to use the definition of acceleration. So the acceleration is 9.8, and that's equal to v final, which is what we're trying to find. And then the initial speed, starting from the top, is going to be 0, and then the time is going to be 1.5. So we get 1.5 for our final speed. Our final speed is 9.8 equals 9.8 times 1.5, which is 14.7 meters per second. So that's the speed with which he left it, and with which he threw it up in the air, and that was in an upward direction. Now, it's worth noting there is more than one way to do a problem like this. I mean, you could have considered the whole trip to find the speed with which he threw it in the air, and use a sign convention that way. You could have considered just the way up to find the height. As long as you figure out a way to work the problem that you understand, that you know makes sense, you're all good. Okay, so let's look at number 26. And this is Giancoli number 26. It says, in coming to a stop, a car leaves skid marks 92 meters along the highway. Assuming a deceleration of 7 meters per second squared, estimate the speed of the car just before braking. Now this one, what we want is the initial speed again. And in this one, what we know is the acceleration and the distance. Now here it's important to figure out which way is going to be positive. And it's most intuitive to imagine that the way that's going to be positive is the direction that the car was moving. And so if you draw a sketch, it doesn't matter which way you have it going, but if you draw a sketch and you want the initial velocity to be positive, then the deceleration, the acceleration, which is a deceleration in this case, needs to be negative. But the distance is still going to be positive. So the displacement is plus 82. The acceleration, and that's meters. This textbook has a lot of issues where they use kilometers, so you want to be careful about that. The acceleration is negative 7.00, and that's meters per second squared. And the final velocity is 0. And how do you know the final velocity is 0? Because it says in coming to a stop. So now we want an equation that has d, a, vf, and vi in it, because we know 3 out of those 4 things. Well, let's see if we can find an equation like that. Well, here are the 4 equations that we have to choose from, the 4 kinematics equations. And we want to choose the one that effectively doesn't have time, and that's the bottom one. Sorry for using distance and x interchangeably. They mean the same thing, so just keep that in mind. So we're going to use 2ax equals vf squared minus vi squared. In this case, we have 2. And once you know that everything's in meters and seconds and meters per second squared, we don't need to put units in the formula. You do the conversions before you use the formula. So you have 2 times negative 7 times 92 equals v final squared, which we know is 0, minus v initial squared, which is this, v initial squared. So v initial, if we rearrange things a little bit, is going to be equal to, since they're both negatives, you've got negatives on both sides of the equation, it's going to be the square root of 2 times 7 times 92. So we take our handy calculator, we say, calculator, what is 2 times 7 times 92? And the calculator says, I believe that's 1288. And you say to the calculator, what's the square root of 1288? And your calculator says, I believe it's 35.8887. And you can round that to 35.9. 35.9 meters per second. 35.9 meters per second. That's your estimation of the initial velocity. And that concludes this screencast.